Okay, let's look at a function. How about the function f of x equals 3 to the x, huh? What's f of 2? 9. What's f of 4? 81. Oh, the recycling stuff? Okay. Oh. So f of 2 is 9, f of 4 is 81. What if I wanted to know when 3 to the x equals 10? What input causes this function to output 10? What's this log? What? Log? Are you using wood? Without a calculator, without any sort of technology, no idea, right? But it's 2 point something, I'm predicting. Probably 2.0 something. 2.09. It's probably a good guess. 2.095 sounds about right. But I don't know for sure. It's probably some really weird, crazy decimal, right? But what if I can find the inverse function to the function 3 to the x? Because what kind of things does the inverse function do? Well, what's the inverse? What's f inverse of 9? 2. And what's f inverse of 81? So how could I use this inverse function to solve this equation? Well, isn't x going to be the inverse, f inverse of 10? Right? Because doesn't this function take the powers as inputs and then output the exponent of 3 that made that happen? So if it takes 10 as an input, it'll give me the exponent of 3 that makes 10. Okay? So if I can just find the inverse function to 3 to the x, then I can just plug it in, plug 10 in. So let's take 10. Let's plug 10 into this inverse function for 3, and I get x equals 2.095903274. Boom. So now the question becomes, okay, what is that inverse function? What was that inverse function I just plugged 10 into? And the answer is, it's a logarithm. It's a log base 3. That is the definition of a logarithm. A logarithm is defined as the inverse function of an exponential. Okay? So what is the inverse function for a log base 3? Or sorry, for an exponential base 3? A log base 3. Okay? So here's the definition, here's the notation. So it's a log and then a small number we call a subscript to tell you what the base of that logarithm is. And then the number you're inputting into that function. And then that function will output the answer. I like the way the book defines this. It actually uses an if and only if statement as the definition. What is a logarithm? Well, a logarithm is defined as log base a of x equals y if and only if x equals a to the y. It's a creative way of defining something. An if and only if statement. So you'll have a section on tomorrow's quiz with some simple log statements that you should be able to do without a calculator. For example, what is the log base 9 of 3? And the answer is 2. Agreed? That's wrong. Oh my gosh. I meant this way. What's the log base 3 of 9? 2. There we go. Oh golly.
What doesn't work?
Because it should be 3 to the second equals 9. There you go. See, I always talk about how I think these little tricks are stupid, but it would have helped me there. Have you ever seen people draw those arrows? 3 to the second equals 9. I've heard teachers call that the football play. Like 3 must be a wide receiver or cornerback. Go tackle and hit 2, and then 2 pitch the ball to 9. I don't know. Mr. Ullery coined the famous gopher example. 3's a gopher, and a gopher burrows underground, digging underground, and then when it comes up and pops its head above the ground, 2's on its head. Right? Weird, right? Oh, that Mr. Ullery. Okay. So the log base 3 of 9 equals 2 because 3 to the second power equals 9. All right, I'll try not to mess this up anymore. What is the log base, I don't know, 4 of 64? 3. Good, right? The log base 4 of 64 is 3. So basically, I always ask myself a question. Whenever somebody says, hey, what's the log base 4 of 64? I say, okay, 4 raised to what power gives me 64? And so the answer is 3. So when 64 gets inputted into this log base 4 function, that function outputs the number 3. You can do these on your calculator. If you go alpha window on the newer operating systems, press number 5, you can say log base 4 of 64, hit enter, and it tells you 3. Well, yeah, changes things. We'll talk about that next week, I think. Okay, or you can not use a calculator at all, which you will not have one at all for these problems tomorrow. So make sure you know your powers by memorization, because if you don't, it might make it a lot harder. So, you know, maybe know the first 15 perfect squares, the first 5 perfect cubes, the first 2 perfect fourths. It's not too unreasonable. That's what I have memorized. Yes? So you have all the first 10 perfect squares memorized? What's 11 squared? 12 squared? 13 squared? 14 squared? 15 squared? That's great. What's 2 cubed? 3 cubed? 4 cubed? And 5 cubed? 25. That's good. What's 2 to the 4th? What's 3 to the 4th? Yeah, that's good. All right, you guys are good. Okay, so let's look at example A. What is the log base 2 of 32? So what does the log base 2 function output when it gets 32 as an input? 5. All right, why? Because 2 raised to the 5th power. You should have a lot of the powers of 2 memorized. 32, 64, 128, 256, 512, 1024. So those are more common. So when you see log base 2 of 32, you're like, you might not know immediately that it's 5, but you should identify, okay, 32 is a power of 2. I know that. It's just a matter of figuring out which one. 2 cubed is 8, not 3. Multiply that by 2, that's 16. So 2 to the 4th, no, it's not that. Well, but 16 doubled. There you go. This is ways you can figure out. How about B? What is the log base 3 of 1? 0. Because what is any number raised to the 0th power? 1. Any number except for 0. So any non-zero number, raised to the 0th power gives you 1. So what is the log base 3,762 of 1? 0. What is the log base 3,762 of 3,762? So there are a couple rules that apply to every logarithm. If you plug 1 in, it's going to output 0. If you plug the same number in that is its base, it'll always output what? 1. Those are actually, so if you were to graph a logarithm, I'd start with the point 1, 0. I would then graph the point 3,762, 1. And then, boom, there's your graph of the log base 3,762. You might want to know that one for tomorrow, hint, hint, wink, wink. I'm just teasing. 3,762. Crazy. Now let's start getting a little bit harder. What is the log base 4 of 2? 1/2. Okay, second period got this one right, but when I asked them why, so I'm going to ask you guys why. Why is the log base 4 of 2 1/2? Because what is raising something to 1/2 power the same as? Square rooting it. Good. So then, a lot of people said it's because 4 times 1/2 is 2. right? And if this is really just multiplication, then why would we create a new function called log that is essentially the same as division? Right? So make sure you're not using division and multiplication. These are exponents. So what would the log base 9 of 3 be? Also 1/2. What is the log base 16 of 2? 1/4. Okay, because if you raise 16 to the 1/4 power, if you fourth root 16, you get the number 2. So that's why. Don't confuse fraction exponents with negative exponents, right? They are not at all the same. A fraction exponent means a radical, okay? Let's look at D. What is the log base 10? And is it, whenever the base is 10, do we usually even write the 10? Right? Isn't an log without a base written assumed to be log base 10? In fact, we call it common log. Even your cheapy deepies will probably have a log button, log base 10. So what is the common log of 1/100th? -2, because that is 10 raised to the negative second power, which is 1 over 10 to the positive second, and so that is, in fact, 1/100th. Make sense? Okay. Ready for some hard ones? Good. How about, what is the log base 64 of 1/4? Try that without any sort of technology of any kind. You said it's technology. If it was 3, then that would mean 64 raised to the third power would give me 1/4. So if I raise 64 to the third, it has to do with the number 3. You're on the right track. What is it? -1/3? So if I take 64 and I raise it to the -1/3 power, well, that becomes 1 over 64 to the positive 1/3. And what is the cube root of 64? So that becomes 1/4. Yeah. -1/3. Boom! This is the first of everything. So, the reason it's negative is because of the reciprocal. So if your base, here's a hint. If your base is greater than 1, but your input is less than 1, doesn't your output have to be negative? Right? Similarly, what if your base is less than 1, but your input is greater than 1? There has to be some sort of reciprocal going on. Secondly, ignoring the reciprocal, we go from the number 64 to the number 4. The only way a number big like 64 can become smaller like 4 is if we're actually taking the root of it, not multiplying it times itself a bunch of times. So we've got the negative because of the reciprocal, and we've got the fraction because we are rooting it. And then we discovered that it's a cube root, and so that denominator is 3. Make sense? Yes? No? Maybe? How about this one? What is the log base 2/3 of 81/16? The log base 2/3 of 81/16. Peter. 1/4?
No, 4.
4?
-4.
Well, if it's 4, what's 2/3?
No, negative.
-4. There you go. It is -4. So we take 2/3. If I raise that to the -4th power, well, what does a negative exponent mean? So this becomes 3/2 raised to the positive 4th. Well, 3 to the 4th is 81. 2 to the 4th is 16. There you go. Huh? So this is one of the things, and I you know, you never want to teach this. Like, you never want to look at somebody and say, you know, to be honest, the only way to do this is to just stare at it until it comes to you. But really, there's just some people that can look at that and kind of see the numbers, and the numbers start moving around on the page, and some people just see it. You see 2/3, you see 81/16, and you notice the connection between them immediately, right? Like 81 is a power of 3. 16 is a power of 2, and they just so happen to be the same power, 4. But the thing is, 81, the power of 3 is in the numerator of one fraction, but the denominator of the other. So the only way you can switch them is by making it negative. So it's kind of like making those connections. And you could have done it the other way. You could have had, what is the log base 27/64 of 4/3?
No, it's negative 1/3.
Negative 1/3 again, just like this one. Right? So you notice. So the first thing is there anything I can do to 27 to make 4? No, but I can cube root it to get 3. And hey, if I cube root 64, I get 4. So the thing is, those are backwards, so it has to be negative. So it's a negative cube root. So it's all about what do I do to this to create that. Okay? So problems like this on tomorrow's quiz, no calculator at all whatsoever. So fun. Well, you got one right. What are you all nervous about?
What kind of calculator should we use tomorrow?
I don't know. Bring a cheat sheet.
And fancy. All right.
Fancy. It's probably going to be, pretty much the whole quiz is going to be no calculator at all, but there will be some investment problems on it, in which case I want you to have graph calculator. So I predict it'll be no calculator. Graphing, logarithms, all of that will be no calculator at all. Then when you come to the investment problems, I'll say, last minute of class, okay, get your calculator out. You have 1 minute to calculate the answers. Yes. Yes. So far, the graphing has gone well today. Everybody seems to remember pretty well from Algebra 2, the graphs of logs. Okay. Here are some properties. The log base A of 1 equals 0. We already discovered that. The log base A of A equals 1. We already discovered that. That will become important because that's going to give us 2 points to plot on every one of these graphs. But then there are some other cool properties, like what's the relationship between the function log base 7 of x and the function 7 raised to the x? They are what of each other? Inverses, which one tells me what the graph, do I know how to graph this? So a logarithm will actually be the same exact shape, just in a different orientation, right? But it also tells me that if I compose these functions together, f compose g, what will they simplify down to? So apparently the log base 7 of 7 raised to the x will in fact equal x. That is a hugely important property. Hugely important. Because that, go back to the beginning of the lesson. What can I now do to both sides of this equation, 3 to the x equals 10, to get x by itself? I can take the log base 3 of both sides. Well, what's the left side simplify down to because they're inverses? X. And then the right side becomes, what is the log base 3 of 10, 2.095903274. Okay, so that's actually how I did that earlier. But not only does it mean that, it also means that if I compose them in this order, g compose f of x, I get 7 raised to the log base 7 of x, and that will also simplify down to x. So that way, what if I have an equation that looks like this? What is the log base 3 of x if I know that it actually equals 12? So how would you solve that log equation? Well, in theory, you could raise both sides to the power of what? So if I raise the left side to the power of 3, and I also raise the right side to the power of 3, oops, oh golly, oh golly. What will happen to the left side when you put a logarithm into the exponent of the base 3 exponential? They cancel, you end up with x, and so the answer is whatever 3 to the 12th is. Yeah, what he said. Okay. Yeah, let's go on to graphing. All right. So how are we going to graph this logarithm? Well, we're going to start by graphing its inverse function, because if I can graph a function, I can graph its inverse. So we're going to start by graphing 2 to the x. Is 2 to the x a parent function? Technically, no. Technically, what is the parent function of all exponentials? E to the x. And then I can do some weird horizontal structure squash to make 2 to the x. But in practice, what do I graph as the parent of 2 to the x? 2 to the x. Call it like it's a sub-parent of its own little local family. To me, it's kind of like the Duggar family. Right? Anybody watch 20 Kids and Counting or 70 Kids and Counting or whatever they're up to, right? The Duggars. There's this family in Arkansas that has 20 kids, 19, 20. They've got 20 kids.
They don't.
What?
They don't go to college.
Some of them might go to college. Only one is of the age to even go to college. They're all younger. So they'll probably have some go to college. They make a lot of money from the show. They have other businesses, realty, and plus, like, that's a lot of tax deductions. 20 kids?
You get like a multi-child.
Each kid's a tax deduction.
So you have all these kids. I don't think it's
Yeah. So, well, there's 20 kids. Can one parent really effectively parent 20 kids? No. So if you ever watch the show, what they do is the older kids are basically assigned to some of the younger kids, and they're like the sub-parent. So what you have is some of the older kids are like your 2 to the x, your 3 to the x, your 4 to the x. So like Jimmy, James, Duggar is your 2 to the x parent, and Julie James Duggar is like 3 to the x. And so you got the sub-parent, when really there's one parent. Jim Bob Duggar is e to the x, right? They all start with J. Ginger with a J, I know it drives me nuts.
I feel like we just ran out. Yeah.
Well, they'll keep doing it. They'll just start combining names. Jim Bob, Jimmy James, Jimmy Jam, Jimmy Jam. All right. So we're going to go ahead and graph 2 to the x, keeping in mind that really the parent is e to the x, but 2 to the x does act as a parent of its own little sub-family, right? Like the Duggars. You'll never forget it now. Okay. So to graph 2 to the x, they'll make twins that one. So we got the point 0, 1. And then we got the point 1, 2. Vertical asymptote to the left. Or sorry, not vertical, horizontal asymptote. There you go. There's the graph of 2 to the x, also known as John Duggar. Okay. Is there a John? Who's John yet? Oh. You seem like an expert of the Duggars. You watch a lot of TLC. You probably watch that Honey Boo Boo stuff too, don't you? Oh my goodness. Honey Boo. I've never seen it. We haven't had cable for years, so I don't watch that. My wife does watch the Duggars on Amazon. She buys them.
Oh, she buys it.
Cheaper than paying for cable. Just buy what shows you want. Yeah, we do. Instead of Netflix, we do Amazon Prime. Because we use the shipping a lot. It's the shipping's nice. And for robotics, we'll do the one-day shipping. It's only like $3. You can get stuff like the next day. Order garage door dumpsters for electric robot. All right. So there's your graph of 2 to the x. Agreed? Okay, now how do I take a graph and then graph its inverse function? We flip it, reflect it across the line, y equals x. So how do you actually do that? What do you do point by point? Switch the x and the y. So exponentials have the point 0, 1, so a logarithm must have the point 1, 0, which totally makes sense. What do you get when you plug 1 into a logarithm? 0. Because anything raised to the 0th power gives you 1. Okay? Then we also have the point 2, 1. Because what do you get when you plug into a logarithm the same number that is its base? 1. Like, what's the log base 7 of 7? 1. Okay? So there's your 2 points. Now, if the exponential has a horizontal asymptote along the negative x-axis, what's the logarithm going to have? Vertical asymptote going down the negative y-axis. So we will have a graph that looks like... See, your graph looks like that. And they should look like perfect reflections of each other through this line, y equals x. Okay? Same shape as an exponential, just reflected through y equals x. What is the domain of this function? Does it include 0?
No.
So we got 0 to infinity, not including 0. What is the range? Yeah, the range is all reals. Okay? An exponential cannot output negative numbers. And because of that, a logarithm cannot input negative numbers. Right? That purple graph never goes below the x-axis. You cannot make an exponential function output a negative number. Not unless you subtract something from it, which is a shift down. For that same reason, you cannot input a negative into a logarithm. If you plug a negative number into a logarithm, you should get an error, or actually try it on your calculator. What is the common log of negative 2? The calculator gives you an imaginary. Apparently, if I raise 10, if I take the number 10 and raise it to this imaginary power, I get the number negative 2. It's crazy. So that's why you don't see anything to the left of the y-axis, because you can't plug negative numbers into a logarithm. Right? No matter what power you raise a number to, you're not going to change its value from positive to negative. Yeah. Does this function level off? Is there a horizontal asymptote over here?
No.
No, it actually goes up forever and ever and ever. Will this function ever reach a height of 5,000?
Yes.
Yes, it might just be a couple hundred miles that way before it happens. It's growing. It's constantly growing, but it's constantly slowing down. Well, horizontal asymptotes have that behavior, constantly growing but slowing down. Well, this is not slowing down so fast that it levels off. It does actually constantly go up to infinity, so always getting slower and slower and slower as it does it. Okay? Let me ask you some questions. For the green graph, what is the limit as x approaches positive infinity? It will also be positive infinity. That's what we were just talking about. The graph goes up forever to infinity and beyond. Stupid Buzz Lightyear. What is the limit as x approaches negative infinity? That's a trick question. What do I get when I plug extremely negative numbers into this function? Nothing. Imaginary. Technically, but we'll just say nothing, not reals. So technically, this limit here does not exist. Here's another trick question. What is the limit as x approaches 0 of this function? From which direction? Beautiful, because if I write it like that, what type of limit is this if I don't specify direction? That's a two-sided limit. Well, what happens as you approach the graph, approach 0 from both sides? Well, the graph doesn't even exist to the left side, so the two-sided limit can't exist. Right? In order for a two-sided limit to exist, both one-sided limits have to exist, and they have to be approaching the same point. So that's a trick question. What direction did I mean? What is the limit as x approaches 0 from the right? Negative infinity. That limit is what describes the vertical asymptote this graph has. Agreed? As you approach 0 from the right, the graph goes down to negative infinity. What is the limit as x approaches 0 from the left? That limit does not exist, because the function doesn't exist. Good stuff. So good? Yeah, the function only exists in quadrants 1 and 4. There's no function in quadrants 2 and 3. Unless I shift it to the left a little bit. Okay. Let's just make up a graph. Let's do y equals, how about negative 2 log base, what sounds like a good base? 5 of x minus 3, now let's do x plus 3, and let's say minus 4. Here we go. Now what am I going to graph first? Log base 5. That is not the true parent, it's the pretend parent. It's the older Duggar sibling. Log base 5. Okay? So what does log base 5 look like? Goes through the point 1, 0, goes through the point 5, 1. Vertical asymptote along the negative y-axis. So you get a graph that looks something like that. Okay, now what do I want to do to this parent function in order to graph negative 2 log base 5 of x plus 3 minus 4? Reflect it in which axis? The x, which is going to be clearly different than if I were to reflect it in the y. Ah, very cool. Okay. And then I also want to do what? Okay, and I'm gonna just do those. Call this a helper graph. So this is not my final answer in green. So vertical stretch and reflect. That point did not move. Vertical stretch and reflect. That point's now down here. My vertical asymptote's now all the way up here. And so I now have a graph after stretching and reflecting that looks like that. A little bit more rounded because of the stretch, and the reflection does that. It does vertical stretch by 2 and reflections. We did stretches and reflections in one step. So that point reflects down here and then stretches away. Okay? Then I want to do what to graph my final answer, which I will do in red. Left 3, down 4. Well, shifting at left 3 will move the vertical asymptote, so let me draw that in. Left 3, 1, 2, 3, down 4, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. What? What'd I do? Where'd my graph go? Oh no. Graph, come back. Okay. So use that red graph as your final answer. Make sense? Question?
How would you reflect it over the x-axis and y-axis? Like, what type of solve that?
So that would look, an equation that involves a reflection over the x-axis and y-axis, so maybe negative natural log negative x.
Is that the same thing as inverse? If you reflect it over the x-axis and y-axis,
No. No, it can't be because it's still going to have a vertical asymptote, and the inverse doesn't have a vertical asymptote. So if you reflect a logarithm over the x-axis and y-axis, you're going to have a graph that looks like this. Right? Still has a vertical asymptote, right? The domain is negative infinity up to 0. The range is still negative infinity to infinity. Whereas exponential functions have a domain of negative infinity to infinity and a range of 0 to infinity. Right. A lot of students think they can just reflect across the x and the y-axis, and that accomplishes the same thing as reflecting across the line of y equals x, but it doesn't. You can, like, reflect and rotate, but you would have to rotate 90 degrees in order to turn that vertical axis into a horizontal axis. That was good. That made me think a little bit, though. Good question. Any questions on graphing? Feel pretty good? Do that without any calculator at all whatsoever? I don't think you need. Do you need a cheapy deepy to do stuff like that? Why? What's the cheapy deepy going to do?
Yeah, me neither. We're 64.
Is it really? I didn't know that. Oh, it's not? Oh. Well, then just make sure tomorrow you don't make mistakes. It's that easy.